about the next homework. So most everyone from both sections has turned in homework 1 already. So thank you. None of them graded this week. This weekend. We can hopefully have it back next Monday. If not, it'll be Tuesday or Wednesday. Sometimes it takes me a little longer on the first homework. What you guys will generally find is I'll send you quite a bit of feedback, even if you do pretty well. And that's the way it tends to work in this class. I kind of front load my feedback early on, and then as we go through the problem sets, the feedback will slowly taper off. So everyone will get more or less personal feedback on their homework, which is why it takes this long. Thankfully, my cohort's not so big this year. I know there's a couple people still missing. That's fine. I've already talked to a couple of you. Just make sure to get it in. And remember, if you did the survey, you have an unexcused late absence that you can use whenever you'd like. I want to talk very briefly about homework 2, which has been posted. It's a very different problem set than homework 1. Very, very different. In some sense, it's easier. A lot less math, a lot more thinking. It's an experimental data analysis problem. Focusing on the concept of thermal equilibrium. So the big concept is the idea of thermal equilibrium in this, and it's about testing. The problem set is about an experiment that tests whether a sample is at thermal equilibrium or not. So one of the questions is it at thermal equilibrium? And your analysis will tell you yes or no. Okay. So what does thermal equilibrium mean? And in this example, it's very, very simple. I'm just going to remind you, if something's at thermal equilibrium, it means that the sample has a single well-defined temperature. All right, I can write down. Wow, my computer's blowing up. Hold on a second. You'll be basically measuring the temperature of something and using statistics. And the question is it well defined or not? Right. And another thing to consider in this problem set, this is a linear regression problem. So this is about fitting lines. So you guys, many of you are in the lab right now, have already done some linear regression in the Igor, the first lab. You can use Igor for this, but you can also use Excel. Any statistics tools? Some people said that they took statistics with Christina Morin and learned RStudio. You can do all of this in RStudio. You like R. So linear regression. And again, if you don't know what that means, this means fitting y equals mx plus b to data. So you have to, I gave you some data, you're going to have to manipulate it in order to get it into like a linear shape, and fit a line to it and derive some information about it. 2 more things I want to just mention, really quick notes. Is I want you to, so those are it. I guess I just have one more note. One more note is really, really simple. When you open the problem set, you'll realize it's like 6 or 7 pages long. Most of it's reading. So just make sure to do the reading. To read intro. All right. I walk you through what the experiment is and what it measures. And I set up the problem for you. You should read it carefully. All right. That's all I got to say about that. So there is the only math in the exam other than putting some things in Excel and doing linear regression is you have to take some logs in the first problem and then just do some division. I mean, most of it's just division. So just numerical data analysis, not too bad. This is much more of a conceptual based assignment. I'm really interested in your thoughts. There's lots of questions that try to get you to motivate some ideas and some thinking. Pulling things and ideas out of your numbers. Okay, that's all I got to say about homeworks 2. What we're going to do today is something a little conceptual. It's not really something I'm going to test you guys on in the homework or anything. I want to kind of set the stage for the rest of the class. So I want to move away from ideal gases today. We've been talking about ideal gases or boxes of gases a lot. And I want to tell you today, or at least get started on the conversation about why the ideal gas law is not really a law, but just an approximation. So I want to tackle what we're going to call non-ideality, things that are not ideal, from two different perspectives today. One, we're going to look at it empirically. We're going to look at some experimental data that will demonstrate why gases are not ideal, even at normal conditions, under typical conditions. And then what we're going to do is transition conceptually into the second half of the lecture, going into the next lecture, talking about the sources, the molecular, the chemical sources of non-ideality. What makes a gas non-ideal? Right, very, very conceptual. Just want to kind of understand these things from a chemical point of view. And then what we'll do is tackle them in a more general way. We'll basically zoom in microscopically, think about how things look at each other, talk to each other in a gas. And then we'll look at how to represent those non-idealities by modifying Pivnert, creating a new equation that replaces Pivnert, that corrects for the non-idealities. And then what we'll do is we'll take that equation, that correction of Pivnert, and see what new things it predicts. And what that's going to lead us into, just a little bit of a spoiler, is we're going to basically turn off the ideal gas law. And we're going to assume that now molecules have sizes and shapes. They attract, they repel, turn those things on. And through that analysis, we'll get phase transitions. Right? We'll no longer just have a gas, we'll have to consider solids and liquids. Right? And so just that breaking of ideality will generate that prediction that we have liquids at certain conditions. So then we'll see where liquids appear. How do they appear? How can we model their appearance? And what's the source of the liquid? Okay. So let's start from Pivnert. And let's just do some experiments with Pivnert. In fact, this week in lab, you're going to do a Pivnert experiment. Next couple of weeks, you're going to do Pivnert experiments and look at the deviations from, well, actually, so this first lab this week, you'll use Pivnert to measure the mass, the molecular mass of the gas. And then in the next couple of weeks, you're going to do experiments with gases that explore the non-ideality of gases, the fact that they're not ideal. All right, so you'll see this in lab for the next couple of weeks. So let's look at Pivnert today. And I really like to look at Pivnert from a very specific point of view in this class, which is that Pivnert, we think of it as a gas law, but really it's just an energy conservation equation. Right? It's two different types of energy that are in an ideal gas that are equal to each other. Right? We kind of looked at this somewhat carefully last class, right? We saw that with entropy and heat, that when you pump heat into a system, you heat it up to some temperature, you generate some heat, right? Some thermal energy, and that thermal energy is always proportional to RT. The KT or the RT appear all the time. And so what NRT, all it measures is that if you have an ideal gas at a fixed temperature, you have it in a bath, say, for instance, the atmosphere or a water bath, NRT is the amount of heat that the bath pumps in, right? That's the supplied energy from heat into the gas. And so NRT is the input heat into sample or contained in sample. Right? And what is PV? Well, PV is what the gas does with that energy. Right? You pump in that heat, and what an ideal gas does is it uses that heat to fill the space at some pressure and some volume. And PV is equal to nRT. These have units of energy on both sides. RT is energy, so PV must be energy as well. They have to be equal. PV is the amount of energy that the system uses. It's the work that the system uses to fill the space. So every unit of heat that comes in is used to increase the pressure and press against the walls. Right, so this is the work done by gas. to fill a container using the input heat. Okay. So that's all PivNerd is, right? PivNerd is that you put in heat and you get out volume work. The work done by the gas to fill the space. And they're equal to each other in an ideal gas. Right? So what would happen to this equation if the gas weren't ideal? What if the gas could do something else other than just fill the space? That's what non-ideality really means, as we'll see, is that when you feed in this amount of heat into your system at some temperature, the gas has a choice of things to do. If the gas is a dumb ideal gas, it's got no size, no interactions, then the only thing it can do is fill the space, right? So it's only PV. But imagine the gas could do something else. For instance, what if the gas, molecules in the gas can attract each other? What if they have some amount of space so that when you put so many in there, they start to crowd, right? They press against, they push against each other. Right? There may be additional source sinks of energy. Other things the gas must do in order to equilibrate besides just fill the space. Right? So in a non-ideal case, the molecules may have other things to do, other tasks to fulfill equilibrium. Have other motions, if you would say. That must be fulfilled in order to equilibrate. For instance, what if, for instance, you have an ideal gas, put in some heat, you heat it up, and then you put a piston in. You insert a piston that can move. Right now, it's not going to be just PV is equal to nRT. The amount of heat it's going to supply is PV plus of the energy used to push the piston. It's going to be an extra energy term. So in a non-ideal case, we would again expect on the right-hand side nRT, right? Because we're just assuming that our bath just feeds in heat, right? It's just a dumb bottle of water, a dumb bucket of water. And it's at constant temperature. So all it does is just feed heat in, and that's nRT, right? RT is the amount of heat brought in bath. And so again, the gas is always required to do PV, right? It has to fill the space, and the energy required to do that is PV. So no matter what, that's always on the checklist for gas to equilibrate. It has to fill the space equally. Right? And that's again something you looked at problem 2 in the homework. That basically, that if you give a gas an option to fill a space, it will fill the space and it will fill it equally. That was more or less the conclusion of problem 2, is that the entropy basically mandates that the box is completely filled. So you're always going to have to do PV work because the box has to be filled entropically. But there's going to be some other stuff, right? So there might be some other forces, F sub I, some forces acting on the system that change different motions, that have different motions that make the gas move in different ways. So we could say that there are forces, different forces acting on the system. And each one causes the system to change by some coordinate. So this was dxi is the motional effects of these forces. So the idea is that imagine that you have all of these atoms, right? And they have some attractions to each other. So you fill this box full of the gas, and the gas has to equilibrate and fill the box. It has to do PV, but each of the molecules in the box feel some force against each other because they're attracted to themselves, right? So they have some force, right? So there's some attractive force that they have, and it affects the motion of each of the atoms by some amount, that force, based on their relative distance between each other. The atoms are really, really close together. They may feel stronger attraction than when they're really far apart. So F sub I is that force, and dx sub I is the change in the positions of the atoms. Right? If it makes the atoms come in closer, dxi is going to decrease as you have this new force that comes in. All right, so things that we could expect, different types of forces that we could expect in a non-ideal situation. All sorts of different things. One could be attractions and repulsions. Strain forces, tension, right? Depends on the material. Flow, right? Maybe you have some sort of flow, right? The gas is flowing from point A to point B, right? You have some flow, for instance, things like that, right? So mass flow, right? Lots of different types of things that can be added, right? And these are going to make the energy is going to be divvied up in a slightly different way than it would be in an ideal gas. Because this nRT that brings in is being divvied up between PV and the forces. Right? And so what that would mean is, imagine that you have a regular gas, and the only thing that's different between it and an ideal gas is the gas is slightly attractive. And so you have one new force that interacts between all the atoms. And so some of that RT would be used for this. Right? And so you'll have less energy for PV. And if the atoms are attracted, right, if they're attracted to each other, they want to close in closer. What that means is that, as we'll see, that means the volume decreases and the pressure decreases as well. You're using energy for attractions, which means you have less energy for PV. And therefore, the pressure that you would read out would be lower than you would expect, because some of that heat is being used up in the attractive forces between the molecules. All right, so it's always a divvying up of energy. You only get so much heat, and it has to be spread out over all the possible motions. So any extra motion you may have affects ultimately the P and the V of your gas, right? What you measure in lab. And so a non-ideal gas should therefore show different pressures and different volumes at a given temperature if it were non-ideal, because it has this additional energy term it has to fulfill. So let's see how that actually works in experiments. The idea is that we're looking for deviations from PV equals nRT. So I'm going to simplify PivNerd a little bit. This is a technique that we use in this class a lot. Just rewriting something. I'm going to define a new quantity called the molar volume, which I write as V bar. And this is equal to the volume of the gas divided by the moles of the gas. Right, so we call this molar volume. This is a really nice number for us to use for volume because now it has units of liters per mole. It's a material dependent quantity. And so we can compare how a system, if we have, say, two different gases and we have 1 mole of each, we can look at how they arrange themselves by measuring V bar. If they're in the same size, imagine they're in the same size container and we have the same size moles, but we measure a different V bar, then that means the gases are interacting slightly different. And the way to see this is to think about, what does V bar measure? Well, it measures how much volume you need to fit a mole. So what molar volume is actually measuring is something to do with the density of the gas. Right? How many particles, how much mass do you have per unit volume? Right, but this is how much volume per unit mass or per unit mole. So it's the inverse of density. So as V bar goes to 0, right, that means that if you have 1 mole, and your molar volume is really small, that means your gas is super dense, right? Because you don't need much volume to fit that mole. Okay, so it's a very high density gas. And so we would say that the density rho goes to infinity. It's the inverse of the density. And likewise, as V bar goes to infinity, right, that means you need more and more volume to fit a mole. That means the gas is becoming less and less dense. So this is low density. The rho goes to 0. Okay, so it's just inverse density, right? Remember that typically the way you learn density is mass per unit volume, grams over liters. These are molar quantities, so we don't have to worry about the mass, right? It's just something that is defined for any material, as long as you have moles of it. So you can compare the molar volume of one material to another, because it's only dependent on the moles, not the mass of the material. Right, so this is something I can easily measure in lab, right? I can go into the lab, I can put in a mole of my gas into a container, and I can measure the pressure. Right? So what I can do now is what I can think about is whether if P V bar, now remember I'm dividing by N, so the N disappears on the other side, is equal to RT. Right? So if the gas were ideal, so at constant temperature, right, if I fix the temperature of my bath, PV should be constant, no matter the pressure. PV is just a number for any conditions. For any gas density. All right, what that means is that no matter how thick I make the gas, how close I jam those molecules together, it doesn't affect the gas at all, because there are no interactions. It doesn't matter how close they are to each other, because they don't talk. So what I'm going to do is to go into the lab, and I'm going to measure PV versus input pressure. Okay, so basically I have a fixed container, bulb, that has a fixed volume, and I'm just going to crank up the pressure. I'm just going to keep feeding in gas, and I'm going to measure P times V bar, measure the density times the pressure that I input. Maybe the gas, for instance, I have some way to measure the density. You can do it with a scale, for instance, that's what you're doing this week. And you can measure the mass of it. You know the mass of the container, you know the pressure, you can calculate the number of moles in there, and therefore you calculate V bar. And you just do this with a scale as a function of P. Right, this is what you're doing effectively, this is what you're doing in lab. You're using a scale to measure V bar, because you know the molar mass of the gas. All right, and so let's look at the results. Last class, I drew this by hand and it just took me too long, so I'm just going to give you a plot. What should PV be for an ideal gas at 298? Well, here's a nice number to remember. It's always roughly 22.4 liters. Right? And maybe you remember this from Gen Chem, and Gen Chem, I remember this from Gen Chem, that if you have a gas at a bar, room temperature, right? Atmospheric pressure, you have atmospheric pressure gas at room temperature, the amount of volume you need to fill a mole, to contain a mole, is 22.4 liters. Right? So an ideal gas fills 22.4 liters per mole. All right, I forgot the atmospheres, of course. And let's look at this graph. Sorry, let me put it on a different page for you. Okay, so the ideal gas line is this straight line that I've drawn here that runs through here. And I have three different gases plotted here. And I'll just go through them one by one. You may notice, so these are three different experimental gases that have different labels. I'll label them right now. And you'll see that one deviates positively, one deviates negatively, and one deviates very negative. These three gases, the top one is perhaps the simplest gas, it's H2. The diamonds, which is this one below the ideal gas, is N2. And this one that's very negatively deviating is CO2. All right, so very interesting, right? We have three different gases, all of which are, in some sense, pretty boring. N2 doesn't react with anything. CO2, you really have to work hard to get to react. And of course, H2 can be a reactive gas. It's a strong oxidizer. But generally, hydrogen is not a particularly strongly interacting gas. It's fairly stable. These are stable gases in the atmosphere. But as you can see, they have very, very different deviations. And notice that they deviate effectively both. It's not deviations that are happening at very, very high pressures. We're seeing that CO2 deviates significantly. Yeah, it's not a huge deviation. About 0.1 out of 20. About 5% at 1 atmosphere, 5% deviation, but that's a significant deviation, right? It's 1 part in 20 deviation. So at 1 atmosphere, CO2 fills 5% less space than you would expect. Did I get that right? No, sorry, that's less than that. It's about 1%. Yeah, 1%. Sorry, I'm off by a factor of 10. It's about 0.5%. That's better. Percent. Right. So, but notice that again, we don't really think that much differently about CO2, N2, and H2. They're all small gases. You know, they don't really have much going on about them at room temperature and atmospheric pressure. But they have significant deviations. One is H2 increases and the other two decrease. So not only do they all deviate, but they deviate in different ways. Let's consider that a little bit, right? So we'll think about that. All right, so some notes, I'll just write these just so we can know. All right, what does it mean for H2 having a positive deviation? Well, what that means is that hydrogen fills more space than you would expect. It has a larger pressure than an ideal gas, right? So that means that the gas wants to be, or pushing out, right? The atoms, the H2 molecules want to be further away on average from each other. Against the walls, they're pressing harder against the walls because in some sense it's pushing against itself. Right? So PV is positive here. This means that this is probably some sort of repulsion between molecules. Right? It's pushing things apart. Put a question mark there because we're not sure yet. But we can see that N2 and CO2 have similar deviations, just significant difference in magnitudes, right? So we have to consider both of those things. Why is it that N2 and CO2, in some sense, if H2 is repulsive, that means N2 and CO2 are attractive, right? They fill less space than you would expect. PV is smaller. It means the gas is more dense. It's not pressing against the walls as hard. It fills less space with the same amount of material. For the atoms are attracted to each other. So by that same logic, at least. Traction. Attractive forces. And then there's also a question of magnitude. Why is CO2 less ideal? They're perfectly reasonable questions to ask. Let's see how far we can take this. because these are small deviations, right? 0.5%. You were doing quantitation, you're doing quantitative analysis where you need to have 4 or 5 significant digits on your concentrations. This is a big difference. Right? If you're doing, for instance, this is going to be really important, high pressure chemical engineering where you're doing gas phase synthesis. These deviations can change the energy balance of your process significantly. Right? A percent less energy or percent more energy can be millions and millions of dollars. You're dealing with careful energy balances in industrial processes, right? So it's very, even though these are small deviations, they're super important at large scale, right? Just like how, I don't know if you guys know this, but like removing the catalogs from an airplane, you know, the back of the seat catalogs on an airplane, they each weigh what? 5 ounces a piece, but you have one for each seat over thousands and thousands of planes. Removing that 0.5 pound magazine, they save American Airlines millions of dollars a year. And it's the same idea here. If you have a 0.5% deviation of room temperature, who cares if you're a qualitative chemist? But imagine this deviation continues on. Later on, we're going to look at processes, a very important chemical process in industry, the production of ammonia industrially, where we work at 50 bar. So this, if we're lucky, you need CO2 for that, it turns out. If we're at 50 bar and this deviation is linear, right, you're dealing with a 50% deviation compared to what you would predict from the ideal gas law. Right? That's a big difference. So we need to consider those kinds of things, not 50, like 50%. Yeah, whatever that is, 25%. You'd be off by 25% at 50 bar. This is for perfectly linear. That's a big difference, right? You can guess better than that. So let's look at how this evolves as we go to higher pressure, right? As we start to cram gas together, attractions or repulsions are going to play a bigger role because the gas is more compact. It's closer together on average. So let's look at some gases as a function of pressure, the same concept. We're going to look at a slightly different variable this time. All right, we're going to return to this variable for the next couple of lectures because it's just a useful quantity. Going to define something called Z or Z, which is where I take PV and divide it by RT. This is what's called the compressibility factor. And again, it's measuring the same thing that the previous example measured, but now I can modulate temperature as well, right? So this allows me to think about how PV changes relative to T in one nice number, instead of just PV by itself. So I can think about how Z moves as T changes as well as P, right? So we're going to look at the variance of Z for a gas as we move T as well as P. Right, so Z is a function. Right, this is advantage because Z is a function of P and T at constant volume. Right, so we can consider both. Right, and again, this is a really nice number because it's constant for an ideal gas. Right, for ideal gas, right, PV is equal to RT, so this is equal to 1. Right, so all we have to do is look at deviations relative to 1 to know if, for instance, the gas is repulsive or attractive. So let's look at high pressures first. So first we'll look at Z versus P. As you can see, very, very interesting curves. Right, so these are at constant temperature. I just wanted to say that these are all at, I think these are all at 300 Kelvin. And so let's look a little bit at what's happening here. Let's look at helium, right? Helium is going to be is a very simple gas. It's monatomic. Doesn't, as you know, helium is a noble gas. you know by definition doesn't have a lot of interactions. Doesn't do anything. But you can see that helium, not surprisingly, deviates, and it deviates in a positive way, but fairly slowly compared to the other gases on this plot. Right? And it's deviating positive. What does that mean? Well, at constant temperature again, that means that the pressure you read is higher than you would expect at a given temperature. And so any positive deviation is repulsive, right? If the idea is the gas is being pressed away from the center with some force, the force in the center is pushing everything out, moving the molecules further apart. So again, positive deviations in Z could be referenced as repulsive, and then any negative deviations would be attractive. And what we see is very, very interesting behavior. Helium is just positive repulsion the whole way up. We'll have to explore very carefully why that is. Why is it that helium in some sense never attracts itself? Why does it even repel itself, right? We already know that it's neither attractive nor repulsive. It's a noble gas. It shouldn't have much interactions at all, but it has some, and it's all repulsive at high pressure. Gas helium wants to naturally push itself away. We can look at nitrogen again. Nitrogen is it's not a noble gas, but it's basically a noble gas. It's very unreactive. Nitrogen does have some interactions with itself. We'll talk about them. But by and large, it's a weakly interacting gas. And you can see as well, interestingly, right, it negatively deviates even more than helium. At high pressure, it's even more repulsive. But at intermediate pressures, it's more attractive than helium. Right? That's a very interesting note. Is that here, at this limit, N2 attractive relative to helium. And then at this point, it's the opposite. Right? And then look at methane, right? Methane is the complete opposite. Well, not really the opposite of helium, but it has a very different distinction, right? At intermediate pressures, methane is an attractive region, right? There's a region of pressures where methane appears more dense than you would expect. And then once you get pressure high enough, it increases like methane or like nitrogen. Right? So there is this region here, this attractive region for CH4. Now, you guys should know that like methane is not particularly an interesting gas. And we'll talk a little bit about that. But there's not really a lot of interesting things going on with methane. It's not particularly reactive unless you put it on the flame. You just mix it with oxygen, doesn't really do anything without heat or without spark. Methane doesn't have a dipole moment. It's a non-polar molecule, dipole-dipole interaction. But yet there's a region in which it attracts itself. So what I want to explore today, and I got one more plot to drive this home. First, we have to distinguish why some things repel and why some things attract. Also think about why some things attract and then they repel at different pressures. Okay. That is a question that we're going to have to consider a different variable. Why is it that this is repulsive here and attractive here? What's changing? Clearly, there's a point right here where in some sense methane is an ideal gas again. Right? It's ideal at low pressure, it deviates and then it's back again. But this is just a coincidence, right? So what's happening is that there's some behavior that dominates at low pressure that makes it attractive. And then as the pressure increases, some other force dominates that makes it repulsive. There's some competition. So we'll have to think about what that competition is. All right, and I think it's better to think about that competition from the point of view of temperature instead. So let's look at methane, because the other two molecules really aren't that interesting. Let's consider methane at different temperatures. So it's the same plot, but I'm going to do it at a different T. And I think this plot is perhaps the more interesting. So I'll just draw my Z equals 1 line. Guys. So what do we observe? Well, we observe that as temperature decreases, everything gets kicked into high gear. The repulsive tail at high pressure is more repulsive, and the attractive tail is more attractive at low temperature. And then as we start to heat, it seems like everything starts to get washed out a little. Right? At 600 Kelvin, in fact, there is no attractive potential. It just basically is just always repulsive. It looks kind of like helium. So at high temperature, it looks like a normal gas, a normal weakly interacting gas. I'll draw that here. This is the high temp limit. Right, looks like helium or nitrogen. Right, it's just repulsive. It doesn't really deviate that much, just a little bit. But at low temperature, very, very different behavior. Right, we have a strong attraction, a strong retractive region. And then we have a strong repulsion region at high pressure. Right. So it seems like whatever non-ideal effects that a gas may exhibit, it exhibits it at two different distinct limits. One is at high pressure and at low temperature. Right, so we can actually make a claim, and we'll see that eventually that this is 100% true. What can we learn from this? So our claims are gases become ideal as P goes to 0. Right? Everything is ideal at the far left corner. Right? When gases are basically dilute, they agree perfectly. So that one. And 2, as temperature goes to, as it gets hotter and hotter. You can imagine that as I go from 600 to 1,000, all what happens is the slope gets less and less and less and starts to approach the ideal limit. Everything just starts to fade. Basically, everything gets washed out by the heat. That's kind of the way to think about it, is that the heat dominates. The heat begins to dominate so rapidly that the other effects, the other forces that are exhibited by the molecules are just minuscule compared to the amount of heat that's present in the system. So we'll look at that more carefully. We have to understand the sources of those forces first. We understand where those forces come from, those extra forces that are causing these deviations. We'll have a better sense of how that heat washing occurs. Why is it that everything gets lessened at high temperature? Okay. So we'll think about that a little bit. So what I want to do is, now that I've identified that there are, in some sense, two different limiting cases for my gases I have, for sufficiently complex gases like methane, I call methane a real molecule, not just a diatomic. There is an attractive and a repulsive region. And then for my simple gases, things like helium and nitrogen, there's only a repulsive edge at high pressure. And so I want to explore today, or get started, on where do these things come from. Right? Not surprisingly, these all tie into intermolecular interactions, right? These things result from how molecules talk to each other in a space. When they're close to each other, do they see each other? Do they feel each other? Are those feelings attractive or repulsive? And so we can see very clearly that at low pressure and reasonable temperatures, there is an attractive field of forces, if you will, especially for methane. And then that goes away and something takes over at high pressure. That's repulsive. So what we need to do is identify what are the forces that are attractive and what are the forces that are repulsive, and when do they become important? Why? Before I do that, I want to tell you a little story. Really, really cool experiment. That sets the stage for our discussion about intermolecular interactions. I want to consider the idea of attractions between objects containing electrons. I know that's a very odd thing to say, but I want to be as general as possible. And by attractions, I could also mean repulsions. All right, we haven't defined which one we mean yet. Negative attractions and positive. What do I mean by objects containing electrons? Well, I can mean gas, molecules, atoms. I also think about electrons or solids, right? Anything that's electronic, right? Electronic matter is just chemistry, right? So not just molecules, but anything. Molecules, atoms, surfaces, anything. Of electrons. All right. And what I'm going to show you today is that regardless of what the object is, two things with electrons will always attract each other, regardless of the properties of the material. They have dipoles or any of that junk, hydrogens, negative charges, positive charges. Get rid of all that. Say, I've got an object that has electrons in it. A metal surface or something. Anything that has electrons in it that are bound, right? So like a metal or an atom attracts another one that also contains electrons. No matter what, it's always attract. And there's a really, really beautiful experiment that was done about 30 years ago that proves this. It's a really, really cool experiment, and it sets the stage for why no gas is ideal. Because every molecule and every atom has an interaction with itself. And as we'll see that the distance between those two objects on sets the attraction or the repulsion. And what we'll find is that if you can modulate the distance between two objects in just the right way, put the gas in a specific situation where on average the gas molecules are apart distanced by some amount, and that amount is reasonable, they'll always attract each other. We'll see that as you move that average distance, it either turns on a repulsion or turns off the attraction or makes the attraction stronger. Right? It's all going to be about distances. So this is a really, really cool physics experiment. Very simple, very easy to understand how it works. How it was implemented is a different story altogether, and why it works is a completely different story. But you can get the gist of it very easily. It's very, very simple idea. So this is what's called this is an example or an experiment proving a specific kind of force that's predicted in physics. It's called the Casimir force. It's named after a man named Casimir. And I'll explain what the Casimir force is after I explain the experiment. The experiment is like this. The experimenter takes two metal plates that are extremely boring, uncharged, neutral. Think just aluminum sheets of aluminum squares of aluminum metal or stainless steel metal. So he's got a sheet here of metal. And I'll just color it in so we can distinguish them. This is a metal plate. It's electrically neutral, boring. There's no voltage, 0 volts. Boring is all get out. It's just a boring ass plate, right? Can't be any more boring. And to the other side of it, I'm going to attach it to a spring. All right, so I have a small little paperweight here that I'll draw right here that doesn't move in place, just like a fixed object. And I'm going to attach to the back of this metal a spring. Oops. That's not good. My program just crashed. Let's see if I can bring it back. Oh boy. Let's go. Saved. All right, I just have to redraw my stuff. So I've got this like paperweight here, and then I just attach it to a spring right here on the back of the sheet. Right, and I have it set up so that it's floating in space. Okay, so there's no forces acting on this. The spring is at its neutral resting spot. Right, we call it the springs at equilibrium. Spring at rest. So no forces are acting on it. All right, no gravity has been considered, no external forces. All right, so we got rid of gravity. All right, we have it suspended in air. All right, and we've set the spring just right so that the metal plate just sits there and the spring doesn't want to extend or contract, right? We don't stretch it at all. It just sits there. And then on the other side, I'm going to add another plate, exactly the same plate. Oops. And I'm going to put them parallel to each other. All right, so I have two. So this is a parallel plate, same plate, but parallel to the other plate. And what I'm going to do is I'm going to attach it to a motor that allows me to move it back and forth. All right, so there's like a rod attached to it. And then there's a motor here that allows me to move it back and forth. Right, it spins a little rod and allows me to move the plate back and forth. So what I can do is I can measure the distance between the two. Right, so I'm going to measure the distance between the two plates as L. Okay. And what I'm going to do is I'm going to, again, these are totally neutral plates, right? There's no voltage between them, nothing. So there shouldn't be any electrostatic interactions like there would be with two charged plates. It wouldn't create a capacitor. If you're an electric nerd, you would know that if you have two plates at a distance with different voltages, that you can create a capacitor between them and build up a charge between them. You don't want to do that. Right? So these are just boring, neutral, as boring as possible plates. And what we're doing is just moving back and forth. All right, and we want to see if the plates attract or repel each other. So what we're going to look at as a function of the distance between the plates, the force that is acted on upon that spring. Right? If the green plate comes in and the two plates are attracted to each other, it's going to stretch the spring. Right? And towards the green plate. Right? It's going to bring this plate in. So the spring will extend. But if it's a repulsive effect, the spring will contract. If there is no attraction between the two plates, nothing happens. So we're going to consider the force acting on the spring versus the distance. Right? If we can find that the spring force is greater than 0, meaning it's stretching, that means that the green plate attracts the yellow plate. Right? And if F is less than 0, it's the opposite. And if F is equal to 0, no interaction. Now, let me throw it out to you guys. My question to you, I've already in some sense given you the answer to this question. What I've said is that anything with electronic matter, if it's in the right position, will attract itself. But what do you think they find? Well, it's exactly what it says. Is that they find that when they move these plates together and they correct for all the little forces in their experiment, because you can imagine things are vibrating, and you can never keep a spring perfectly firm. There's air, there might be some, even if it's in a vacuum, there might be some flow of gas that might push things, could be vibrations from the room. I know as someone who's done vibration sensitive chemistry, if you're in a teaching building, people running around upstairs in the classrooms or in the teaching labs affect the vibrations in their lab, and you can notice it in these very sensitive things. For instance, in laser labs, we have tables that have air suspension to avoid those vibrations. So you have to damp all these things out. Right? So once you account for that and you bring these in, you see something very, very beautiful. And I want to show you the exact result from the actual paper. It's one of our supplements that I've posted on Canvas today. You don't have to read it if you don't want, but I think it's kind of cool. And this exact thing that I've just described is exactly what this experiment did in 1996. A single man did this experiment. And what he finds, so he has a very, very complicated setup that's basically exactly what I explained to you. This is two plates that have one has adjustment rods, the other one's on the spring. And there's a very, very complicated set of circuit to cancel out all of the electrical effects, right? So the electrical circuit just turns off the electricity, cancel it out. And this is what he finds as a function of distance. Right? As he brings the plates closer together from 10 microns to about, what is this, about 200 nanometers, he finds that there's a positive force. What does that mean? That means that the plates are attracting each other. All right, people have done this experiment since 1996. People have done this experiment over and over again. In fact, I showed one on the other class. They take two stainless steel spheres, and put them together, and you find that the spheres, like two atoms, just balls of electrons and nuclei, two spheres attract each other in the same way as well. So there's a positive force regardless of the material. If you get these two electronic containing materials together close enough, they will attract themselves. And this is a completely universal effect. I'll go ahead and copy and paste this in, and then kind of write down my conclusions. This is a very, very small force. It's not very strong. Plates are attractive. On the scale of about L equals a nanometer, or sorry, 1 micron. Okay, 1 micron. That's pretty close. I mean, we're talking about the width of a hair. This is less than a width of a hair. We're talking about tiny, tiny amounts. But they attract each other very, very weakly. And this is universal. In fact, what Casimir predicted in 1940, Casimir predicts "60 years before, that the force felt by a plate divided by its area," so this is the area of plate, and this is the force felt, attractive force, is equal to minus hc pi squared, these are just numbers, divided by 240 times the length, the distance L to the 4th power. Right? And that's exactly what they see here. This, if you fit this to a function, this function right here goes as 1 over L to the 4th, just like we predict. So what Casimir says, and he predicts this with some crazy math that we will never cover in this class, far beyond the limits of us, but what he shows said if you have two materials with bound electrons in them, just like metals, any sort of atom, molecule, there is an universally attractive force between them. Every atom attracts every other atom, at least at some distance. Attractions are entirely universal. That should give you pause for a second, because I just showed you examples of where things repel. Right? So there must be some other force, right? I've just described an attractive force that is universal. So it says that no matter at what distance, we should be able to absorb some attraction between them. But as you saw with helium and nitrogen, you didn't really see that attraction in them. That doesn't mean it's not there. See that all it means is that it's completely consumed by something more repulsive. There's another force in the mix. Right? We have to identify those forces. But this is a universal one. And we're going to find, not this class, but next class, that this force you guys knew in chemistry by a different name. This universal force was discovered in molecules years ago. It's called the van der Waals force. Right, so van der Waals interactions are the chemical version, the chemical equivalent of the Casimir you find in metal plates and surfaces. All right, so we'll talk about the van der Waals force from a chemistry point of view next class. Okay, but this is what the Casimir force is, and that's why we see van der Waals forces in everything. And one of the great examples of where the Casimir force plays a big role. So in a really, really dumb experiment. You guys are probably too young to really appreciate this. But back in the day when people had like regular phones, we had these giant yellow page books. We had really yellow pages. And they used to be like 600 pages long and giant tomes of phone numbers made out of this shitty, thin toilet paper. Right? That each page, if you sneezed at it, it would rip. But if you tried to rip 100 of them at a time, right? Like Brock Lesnar could barely do it himself, right? Like, or even the whole book in half, right? So somehow you've taken 700 completely paper thin Scott toilet paper pieces of paper, and you've crammed them together in a book. Each one of them, or each pair of them, no attraction between each other at all. You can rip them as if they're nothing. But when you take 700 of them and try to rip it, it's a lot harder to do it, right? You got to get the world's strongest man to do it. Sometimes they can't do it. Why is that? Well, it turns out, and it was I wish I could find the paper, but I found it at one point when grad school was really bored. Someone did a study on this. They went and calculated the rough separation between the average papers and the gravitational potential between pages of a yellow page book. Right? Consider the material, which is again graphite. It's just mostly carbon, right? It's cellulose. When you think about the average distance between those pages in a typical 700-page yellow pages book, and you calculate the Casimir force between each of the pages across all 700 of them, and you realize that the force that you have to break is almost exactly the amount of force that's required of you to rip it. So what you're seeing is an accumulation of very, very large amount of surface area, right? Every pair of pages pushed together, 700 of them, accumulating these Casimir, these very, very weak van der Waals forces between the sheets of cellulose that by themselves make no difference. They're almost negligible. But when you have thousands of them over thousands and thousands of square feet of surface area, it accumulates a lot of tension and force. It's very hard to break. So these forces are macroscopically extremely important, but by themselves, they're very small, right? So that should give you a sense a little bit about the distance scales and the pressure scales. So when we have a macroscopic bulk, like a bunch of cellulose pages, these forces are extremely strong and macroscopic, but when we're in a dilute gas of helium, they might not matter so much. So there's a sense of surface area. It's really important, etc. Okay. So I'm just going to very, very briefly introduce the next topic, and then I won't even jump into that. right? We have to, in some sense, accumulate and catalog the forces that are available between molecules. So our goal next class is to catalog the common forces between molecules and atoms. We know that for a fact that there is at least one that we know of. Right, the Casimir or the van der Waals force. Right, we know that this is universal, but it's also very weak. So, in fact, if it's universal and weak, right, let's go back to our plots. I kind of was driving this home, right? If we look at our different gases, they all feel the Casimir force between each other. Helium, nitrogen is attracted to nitrogen through the van der Waals force. Methane is attracted to methane through the van der Waals force. Helium is attracted to itself through the van der Waals force. The question is, how attractive are they to each other? Is the strength of helium to itself stronger than nitrogen to itself? Right? You think a little bit about the relative strengths of things. But that still doesn't explain why methane has this attractive potential and the other two don't. They all have the same force in common. But methane in particular seems to have more of it, of this attractive force than the others. Why is that? Right, so there's some molecule dependence to this force. It's not necessarily just about surface area like it is with the plates. If we go back to the plates, the force for the plates is only dependent on the length, the distance between the two. Right? That's clearly not the case in our molecules. Right? Because if it was only dependent on the distance between the two, then they would all roughly have the same behavior. They're just gases. So something else is going on. There must be a new attractive force, some additional attractions in methane that aren't present in helium and nitrogen. Okay, that isn't necessarily satisfied by just the presence of van der Waals. There has to be something else in there. And you may also consider, if you're a particularly savvy chemist, you know I've picked extremely boring molecules here. What if I put water on this scale, for instance? Or formic acid, something that has hydrogen bonds, something that's very polar, acetonitrile, chloroform. Think of different solvents, for instance, and things that have dipoles and electronegative atoms. Where do they fall in this category? Right? Do they have significant deviations, or do they act like methane? Do they act like helium? So there's more things we haven't considered yet that's going to play roles in that'll play a role in determining attractions and repulsions and non-ideality that we're going to have to kind of uncover. So there are other stronger attractions are present. And a really good example of this is the comparison of H2O and H2S. What phase is water in at room temperature and atmospheric pressure? Do we drink it or breathe it? Come on, someone. This is a dumb question. Come on, it's an easy one. We drink it, right? So it's a liquid. Right, so at 298.1 Kelvin, this is the liquid. Does anyone know what hydrogen sulfide is at room temperature and room pressure? It's a gas. Why is that? Right? What do we know about sulfur and hydrogen? They're in the same part of the periodic table, right? They're in the same column. They're isoelectronic to each other, right? O and S are isoelectronic. They have the same number of valence electrons. What do we say about atoms that have the same number of valence electrons? They react similarly, right? They have similar chemistry. But as you can see, H2S is not a liquid. Liquids are things that have lots of interactions. We'll see interactions, right? And we know a classic interaction in water is the hydrogen bond. And then at H2S in the same conditions has no interactions. All right, so there's something chemistry specific about the interactions. All right, we'll have to think about that. Specificity. I think I spelled that right. Yeah. Chemical specificity. Chemistry, that's a bad English. But regardless, right? So there's something chemical about it too. It's not just some, right? There must be some like universal force, but it exhibits itself differently in different molecules. And then finally, the thing we haven't even mentioned are attractions, but we saw repulsive behavior. I haven't even mentioned anything repulsive. So what are the repulsive forces? Right. So I'm just going to write that at the top. Where the hell are the repulsions? We know that they repel, but where do they come from? And it turns out that there is a repulsive force in chemistry. You've never heard of it, never thought about it. It turns out, so when you, as we'll learn next class, one of the great examples of this competition between attraction and repulsion is hydrophobicity versus hydrophilicity. If you take in biochem, you've heard this term 1.5 million times. You work about fatty, membranes, for instance. You have a fatty acid side and or you have a fatty chain side and an acid side. One's hydrophilic, one's hydrophobic. And the way that we often think about hydrophilicity and hydrophobicity is that in some sense, hydrophobic regions repel water and hydrophilic regions attract water. This couldn't, in some sense, be further from the truth. Hydrophobic and hydrophilic regions both attract water, but it's always about competition. It's about the fact that hydrophilic regions are more strongly attracted to water than hydrophobic regions. All right, here's a good example. We'll show next class that when you take a water molecule in the gas phase and dimerize it, meaning you connect it to another one through intermolecular interactions, you form a hydrogen bond, and that's very strong. Hydrogen bonds are extremely strong. Right? That's what we would call a hydrophilic interaction. You have two water molecules, they want to bind next to each other, right? And they have very strong attraction. Or for instance, formic acid in water. Very, very strong attraction to hydrogen. But what about methane in water? Methane is hydrophobic, right? It's a hydrocarbon, or ethane. You can take any hydrocarbon. And say, well, does that mean that when I mix it with water, say I take a water molecule in the gas phase and my methane, do they also attract? And the answer is yes. Methane water does have an attractive bond. Not a bond, but an interaction. They do attract each other. It's just that the attraction water has to itself is greater than the attraction it has to methane. So if you think about oil and water interfaces where you mix olive oil and water, what happens? They separate. That doesn't mean the water is repelled by the oil, not at all, but rather that the water is more attracted to itself than it is attracted to the oil. And as we'll see, that by and large, every interaction with everything is attractive. Very few exceptions where things are net repulsive. Very, very few exceptions. It's just that in chemistry, we always have competitions. And when it comes to things like this, what we're really talking about is what's more attractive to what than the other thing. It's about relative attraction. And as we'll see, there are very, very few repulsions. I'll give you tons of examples next class of things that you would think should not be attracted to each other, but they are. That's because everything attracts to itself. It's just that some things don't attract to themselves as well as they attract to others. Okay, so we'll talk about that relative stability and relative attractions next class and identify these different interactions. Okay, have a good one, guys. Hi. That's okay.
But,
Yes, it is. She's in this. Do you remember when Kayla's hours are?
today,
Yeah, today,
45.
4 to 5 in the CLR. Can you not make that? You can make mine tomorrow though, can't you?
Uh,
You don't know, 10 to 12. You can make what?
I can.
Well, that's fine. Not many people are coming to my office hours, so you can just come when you can. I'll be in my office. Oh, okay,
That is like in certain windows.
okay. So that's fine. That obviously takes priority.
It's tough because I have practice usually from like that 2:30, 3:00 until it's 5:30.
Okay. Right. So that means that you can make tomorrow's section. Tuesday's section with Kayla and Allison. That's at 6 to 8, I think, or something like that.
Yeah.
Okay. So you have some time around noon tomorrow then, is what you're telling me. Noon or 1? I'm sorry?
Noon is when I have to take the test.
Noon's when you have to take the test. So I'm available tomorrow at my class is at 3:30. I like to eat lunch by 3. So if you're like, yeah, is there any period in there from like 10 to 2:30 that you can meet? You want to try 2?
I could meet for like 45 minutes from 1:45 like.
Let's do that then. Let's do that. I'll be up in the PChem lab at that time tomorrow. Just come find me there, okay?
Sounds good.
All right.
Thank you.
You're welcome. Hi, what's up, ladies?
Tried so hard on that last problem
Okay,
and I kept getting one.
you kept getting
I
one.
kept getting one and I was about to jump off a cliff.
Do you have it with you right now?
I do.
Can we go sit outside in just a minute once I clean up and just go look at it?
Yeah.
Yeah, of course.
Yeah, cause I was like, I went to you and then I was trying to explain it to Jade. And then I was like, I set it up and you said the setup was good. And then I got one
You got one.
instead of 1.02. And then I just kept getting one for the rest of them. Everything was.
Yeah,
fine.
they should be 1.02 and then 1.22 and then I think 20 or something like that.
It was
All right,
one.
well, we'll look at it carefully. Hold on. Be close up. It's okay. I'm done for the day, so I have some time to kill. I don't have anywhere.
I'm trying to choose it.